So we're going to be using our exponent chart to help us. So keep that out and handy on your desk. So the notes, the title of the notes are nth roots. That's how you say that. Nth roots, like the seventh. This is the nth roots and rational exponents. So what is n for like nth? N is just a number. It's just a number. It could be anything. It's just a number. So instead of saying the first, the second, the third, the fourth, you can say the nth, and it could represent any number. It could be the seventh of something. And so we could use it to represent either raising a variable to a power or taking some root. So finding the square root of a number, so it's not the nth, it's the second. Finding the square root of a number and squaring a number. Oh, I should have had those switched. I don't know. That doesn't make sense the way it's written. These should be switched. Finding the square root of a number, and it should have been that. And squaring a number, it should have said that. They're what kind of operations? Starts with an I. Inverse. What do inverse operations do to each other? Do what? Yeah, kind of. I don't know that they're mirrored, but they do something to each other. If I square a square root, or if I square root a square, what does that do? They undo each other. They undo each other. So we need to know what inverses do. Inverses undo each other. They like cancel each other out. If you add 4, but then subtract 4, you're not changing anything. It undoes itself. And so the inverse of raising something to some power, some nth power, so it could be to the 5th power, is taking the nth root. So if it was to the 5th power, it'd be taking the 5th root. So here is just an example, and I'm going to show you what these names are. Now up here, I put square root and I put a little 2 there. Do you ever see a 2 there when you see a square root? For some of you, that might be the first time you've ever seen a number there, other than maybe a 3. Normally the 2 is not written, it's implied. So if you see the root symbol and there's nothing, then it's a 2. But that little number right there, it has a special name. That number is called the index. So the number that is sitting on the little seat of your square root, or your root, sorry. The actual root symbol, it's called a radical. And the number underneath the radical, or the stuff underneath, is called a radicand. This is also a root. So this one would be a 3rd root. Okay, this one will be a 3rd root. So far, so good. To simplify square roots, we will try to rewrite things using the second power. So to simplify square roots, so square roots are like that. We're going to try and rewrite things to the second power because those undo each other. So when I say it undoes it, it doesn't mean that like the whole thing disappears. If we think about a different operation, if we think about an operation like 7 plus 4 minus 4, well, I have 7 and I'm adding something and I'm subtracting something, but what am I left with? 7. So what you started with, it doesn't disappear. So if I have x squared and I square root it, I'm not left with nothing. I'm left with whatever that thing is that you're starting with. So for the first 3 examples, we're going to try and rewrite things to the second power because we're square rooting. Again, if there's no number there, the number is actually a 2. We don't write it, but that's what it is. The next set of examples, we've got a 4 and we have a 3. This one has nothing, but what is it? It's a 2. If there's no number there, it is a 2. Okay, here's how your chart will help you. So on your chart, if we're doing square roots, we're going to be looking down the square column. So we're going to be looking down this very first column where we're looking at things that are squared. And so if we have 81, we're going to look down that square column. Is 81 in that square column? Yeah, because it's what squared? 9. So I'm going to rewrite this. This is how you show me that you know what you're doing. So I have the square root of 9 squared. And here's where something is tricky. We struggle with exponents. So I'm going to show you that this is the same thing. You don't have to write this down. I'm just going to show you. If I have, bless you. If I have x squared, let's say I'm doing a box or something like that. And one part that I have to multiply is x squared times x. What does that equal? X to the third power, right? So when you multiply, you add exponents. So that equals x to the third power. Why did I even show you this? Because if our goal is to rewrite stuff to the second power so that we can cancel out operations, that is to the third power. Those don't cancel. But what if I rewrote it like this? It still equals x to the third. But if I rewrite it as x squared times x to the first power, that one can now cancel. So we want to try and rewrite everything that we can. Not everything is going to simplify. We just want as much as we can to simplify. And then the x to the third power is the same thing as x squared times x to the first power. There's other ways that we can split up exponents. That is one of them. So anything that I have that's underneath my square root that's raised to the second power, square rooting it they undo each other. So this one is undone and this one is undone. And so that means that this part can be rewritten out into the front. And then you write down what you have left. All I have left inside is just an X by itself. Now, I don't expect that anybody could, again, get this question as a quiz question right now and that you could answer it and you would feel good about it. But can you at least give me like jazz hands? I sort of can follow along. Yeah? Can we sort of follow along? Okay, even if you couldn't do it by yourself, you can look at what I did and sort of follow along. Okay, that's fine. The next one, we're still square rooting. So our goal is to rewrite things underneath the radical as something squared. So we're going to use our chart, that first column again, to help us. And you're looking down the column, is 75 anywhere in the x squared column? No. Okay. So our second step, if it's not there, we're going to think about, could one of these go into 75? One can, but that's not going to be helpful. Could 4 or 9 or 16, 25, could any of those go into 75? And the biggest one you can find is what you want. So is a 75 divisible by anything in that square column? 5 is not in that x squared column. 75 can divide by 64? No, it cannot. 25. You see 25 in the square column? Okay, well, 25 times what gives you 75? So let's rewrite this. We have the second root, 25 times 3. Well, as it's written, it doesn't help me all that much because I want to see things as something squared to identify that they're canceling out. So I could rewrite it. Isn't 25 the same thing as 5 squared? Yep. And so if I am squaring and then square rooting, that's going to cancel and move me outside. I probably should have been more specific with what happens when they cancel. So the 5 goes outside. And then I write down what I have left. And here's a trick. We just figured out what the square root of 75 is, what it reduces to. Chances are somewhere today, if it's not on the notes again, it's probably on your homework again. There's a lot of common square roots. We need to know how to simplify that or to rewrite it. Don't go through all the steps again. You can go look back at something you already did and use it. For the next one, we have no numbers, but that's okay. That is okay. So what I'm going to show you is that, again, what do we want to try and rewrite things as? To what power? Second power, okay. So 5 is the same thing as, because you add exponents, if you kind of chop it up. Let me show you another way to just visualize this. I need more room. I'm going to write it right underneath. So for those of you that are visual learners, I will show you. So I'm going to write the X part 5 times. And then I have the Y part 8 times. And then I have a Z. So I know that every group of 2 makes a squared. So I'm going to figure out how many groups of 2 that I have. So for my X's, looks like I have 2 groups of 2 for my Y's. We're just rewriting how many of them we have. So is everybody good with this first step? It's just rewriting it, and standing on it. So what we do now to figure out how many groups of 2 I'm gonna have, if I'm starting out with 5, it's kind of like asking, like, how many times does 2 go into 5? Well, 2 goes into 5 2 times, and then I have 1 left over. How many times does 2 go into 8? 4. So I should have 1, 2, 3, 4 groups. So that's what you're doing. You're figuring out how many groups of 2 that you have. So if I have 2 x groups, I can pull it out and it's an x to the 2nd power. If I have 1, 2, 3, 4 y groups of 2, I can pull it out and it's y to the 4th power because there's 4 groups of 2. And some of you guys will get to where you don't have to expand it to see that. And some of you need to do that, and that's okay. So I have 2 x groups. I have 4 y groups. And what I have left underneath my square root after I do that is just an x and a z. And I'm only writing the 2 there so that I can remember what kind of exponents I need. In your answer, you don't have to have the square root. Any questions over our first 3 examples? Again, it's okay if maybe you need a lot more practice before you can do it on your own. But is there anything that you have a question on? Okay. Well, we're going to do the same thing if we have nth roots. So for the first one, it's a 4th root. So what do we want to try and rewrite this stuff underneath the radical? We want it to the what power? If it's a 4th root, we want it to what power? The 4th power. So this time we're not looking down the square column. We're looking down the 4th root column. We're looking down the 4th power column. So let's see how we can rewrite this. And the little number, the index, is not optional. You gotta write it. The only time it's optional is when it's a square root. All right, for 81, is that in the x to the 4th column? Okay, so 81 is what to the 4th power? 3 to the 4th power. And then x to the 12th power. How many groups of 3 can go into 12? 4. So this is the same thing as x, and I have 3 to the 4th power because I have 3 groups. Anything that is to the 4th power, it's gonna cancel out that operation and I can write it out into the front. If I take both of those things out, what is left underneath the radical? Nothing. I just took everything out. So it's okay if the radical totally disappears. So whenever the power goes in there evenly, like 12 divided by 4 goes in there evenly, you can rewrite it like this. For part E, what do I want to raise these to what power will help me cancel things out? I'm taking the 3rd root or the cube root. So what power do I want the things under the radical to be? So let's look down that cubed column. Things to the third power is 64 in the third column. Hello. I do not. I have not seen her in a minute. No, I haven't seen her in a while. So 64 is what to the third power? All right, x to the 15th. Can 3 go into 15? How many times? 5. And if you're confused about which one goes inside versus outside, you want the one outside that's going to cancel. You could write it flipped and it makes the same number. Hello? She got a schedule change, so she's in my 6th period, so she's got to be somewhere else right now. Hold on, what did you say? Oh, okay. Yeah, no problem. And then what about y to the 7th? So does 3 evenly go into 7? No, it doesn't evenly go. So I got to think about, okay, well, how many times could 3 go into 7? Twice. So I have y to the 3rd and then y to the 3rd. And then I would have one y left over, right? Because that's 3, 4, 5, 6, and then one more would be 7. So I don't have to write it out all the amount of times like this. I can kind of abbreviate it here. So anything to the third power, it is going to have it cancels the operation and I write it out front. Cancel, write out front. So I write down what I have. I have a 4 that goes out front. I have an x to the 5th that gets written out front. And I have 2 y's. And then I write down what I have left. That one away, that one away, that one away, that one away. So I'm left with just a y. Are you sort of starting to see the pattern here? We rewrite and we cancel things out. Yes, no, yes, ma'am. Oh, so where I have this part, 15. So if this index can go evenly here, it's 15 divided by, that's an even number, right? 5. I can write something to the 15th power as the same thing as the 5th power, all raised to the 3rd power, because when you raise an exponent to a power, you multiply these two numbers. So 5 times 3 is 15, so I can rewrite that. And it doesn't matter what's inside. Anything that's to the 3rd power will cancel. So you're left with just what was inside. F. F is a trick question. Can you take the square root of a negative number? No, you can't. You cannot take the square root of a negative number. So let's make it positive, and now let's evaluate. You can't take the square root of a negative number. It's not possible. Good news, I'm not going to give you the square root of a negative number on a quiz, on a test, on anything. So I do need to make sure that you know that. But let's go ahead and do this problem as if it were positive, because you can't take the square root of a negative number. So first thing that we're going to have to do is rewrite things to what power? Second power. Well, let's look down the x squared column. Do we see 125? No. Is there something in the x squared column that you could multiply by to make 125? So Ella's got it. Who else can see one of the perfect squares that can multiply by something to make 125? Oh, wait. 5 isn't in the x squared column. That would work. So I'm going to rewrite this as 25 times 5. And then x to the 7th power. 2 can go into 7. How many times? 3. It doesn't go in there evenly, so I can't write it like that one. But I can do x squared, x squared, x squared. And then I would have 1 x left over to make 6. And then what about to the 6th power? Does 6 divide by 2 evenly? Yeah. So we want it to be something to the 2nd power, and it's y. So it's 2 times what gives you 6? 2 times 3. So the 3 goes inside. So I'm going to rewrite this one more time, just showing that the 25 can be rewritten. So anything that is raised to the 2nd power, it can be rewritten out front. So you rewrite them out front. I've got a 5. And then I have 1, 2, 3 x's. So x to the 3rd. And then I have a y to the 3rd. And then I write down what I have left. We'll go underneath the radical. I have a 5 and an x left over. Hopefully you guys are starting to see the big picture, what it is that we're doing. We're rewriting things so that we can cancel. The last section on this front page is going to have us combine radicals. Well, radicals or roots must be alike. It's having it's the same thing as having like a common denominator. They must be alike, the same, common, to add or subtract. It's just like adding or subtracting fractions. So when we look through here for part A, these two are alike. They both have square root 13, but this one has square root 5. So these two are alike. This one is different. If you have one that's different, you have to ask yourself, could I change the square root 5? Could I simplify it in some way to make it the square root 13? No, not gonna happen. So the only thing that you can put together are like radicals. So you can put together square root 13 with square root 13. So this says I have 4, and then I'm going to add 3. So if I have 4 and I add 3, how many do I have? Yep, so I have 7 square root 13. And the square root 5 cannot combine. It just has to be by itself. So if you have things that are, it's like having an x squared and then an x. They just cannot be put together. They have to stay separate. So if they're alike, you can put them together. If they're not, you can't. For the second one, the cube root of 16 and the cube root of 2, are those the same? No, they are not the same. So we cannot put them together unless, and usually it's looking at the bigger one. So the cube root of 16, could we maybe rewrite that? Sure. So let's take a look. If we wanted to simplify this, we would have to find something that we could rewrite to the third power. So looking in the x to the third column, can I find 16? No. But is there something that divides evenly into 16 that's in the x to the third power column? 8. 8 would work. So I'm going to take that and I'm going to start simplifying it. 16 is the same thing as 8 to the third power. Not 8 to the third power. 8 times 2. I'm not doing anything with the second radical. And then I know that 8 is in the cube column. It's the same thing as 2 to the third power. Two to the third power. If I'm cubing a cube root, it can be rewritten out into the front. So I get 2 in the cube root of 2. Now, do I have two radicals that are alike? Do I have alike radicals? So they not only have to have the same index, so they're both cubes, sorry, cube roots. They're both the cube root of 2. So yes, I can put them together. So if I have 5 and 2, then how many do I have? In the first example, did I add what was underneath the square root or did it stay the same? Same. What about this one? They were both cube root 2. Did it change? No. When they have to be the same, in the answer, they stay the same. When you add them, they don't change. For the last one, I have 12 and 27 and 72. Well, I'm going to have to look through each one and see if I can reduce them. So for the first one, these are all square roots. So I'm looking down that square column. Square root of 12, square root of 27, square root of 72. None of them are in that x squared column. So what I have to look for are multiples, things that can go into 12 or 27 or 72. So for 12, what perfect square could go into 12? 4. Good job. So this is like 4 times 3. So looking down the x squared column, what perfect square can divide evenly into 27? Nine doesn't have a whole lot of factors. So what can multiply to give you 27? It has to be in the x squared column. 3 times what? Yeah, and 9 is in that x squared column, so that works. 9 times 3. Let's see. So in the last root, 72, that's also not in the x squared column. But is there a perfect square that goes into 72? There is. Something times one of those will give you 72. 36. Okay, so now I'm gonna rewrite these. Because that's 2 squared. And 3 squared. And 6 squared. So remember, anything that is squared can rewrite out into the front. This might be the first time that we've rewritten something out into the front and there was already something there. When there's already a number there, they multiply. So I'm pulling out the 2 because the squares cancel. So it's 2 times 5. And then 3 times 2. And technically, this is like 6 times 1, which is out here. So now, after I've simplified, do I have any like radicals? I do. Can I put everything together? No, they don't all go together, but I can put any of the square root of 3, those are alike, so I can put them together. So if I have 10 and I add 6, then I have 16. And I cannot put square root 3 and square root 2 together. They're not the same. They have to stay apart. Good news, the back is a little bit shorter. But we've done a lot of math so far, so welcome to the animal show and tell. So take a deep breath. Maybe we can let go of a little bit of stress as we look at some of these cute animals. Thank you to those of you that sent me stuff. First, who can tell us who this is? Who is this cute little guy? Well, I don't know. Is this a boy? I think it's a boy. Who is this guy? What do we call him? What a cutie. He likes to smile for the camera. And next we have, who can claim this one? Whose animal is this? It's a black cat. Who owns a black cat? This is a stray? Nobody's gonna claim this cute black kitty? Who's black kitty? That black kitty is brokenhearted. Nobody's even claiming the black kitty. Okay. The next one isn't a real animal. It is a I wish animal. And who wishes they could have a monitor lizard? It's a weird wish, my friend. As a weird wish. But listen, to each his own. Maybe one day you can get you one. My son is a father of dragons. He's got 2 dragons. What are they called? Why am I drawing a blank? Yeah, nope, he doesn't have those. Why can't I think of what he has? They're bearded dragons. And he's got this little leash that he can put on it to have it walk. And it's got wings. So when it walks, it's got little wings. Oh, I'll have to have him send me a picture. So this one, I think that's Giovanni's and she's not here, but that is her cute little kitty. Somebody else with a black cat. Who's going to claim this black cat? Your black cat. What do we call that little black cat? Jenny the black cat. So nobody wants to claim this black kitty. No kidding, right? Why doesn't anybody want this black cat? Well, that's a bummer. I think they're here. I'll have to double check on that one and call you out for being a traitor to your own kitty. All right, I have some animals. Can you tell which one is my favorite? Yes, my big fluffy white dog. So he once was little and then he growed up. He was like 3 months there, but then he got huge. It's a Great Pyrenees, but this is like 3 months old. So he got really big. He's like 100 pounds now. We also have a kitty. The kitty thinks it is a dog and goes on walks. There's the kitty who doesn't really like when Jackson sits with him. The cat is Savage. My big white dog is Jackson. We also have Bella. But those are our puppies and the kitty. Okie dokie, on to the back. So on to the back. This says that roots can be rewritten as rational or fraction exponents. That fraction exponent on that pre-quiz, were y'all like, what the what? What is she doing? Did anybody wonder, like, why do we have a fraction as an exponent? We can take and we can rewrite rational exponents, so things as a fraction that are an exponent. They are the same thing as this. So I want you to look at these two for a second and see where the pieces go. So if you have something to the fraction exponent, if you rewrite it as a radical, looks like the top of the fraction stays, but the bottom gets rewritten as the index. So here's how I remember this. Bless you. What is in the bottom? It gets rewritten out into the front. So when you rewrite it as a radical, it becomes the index. Or if it's the index, it gets rewritten underneath. So that's how I remember. I draw a little kind of semicircle to tell me where it goes. So when I look at the first one, I have 64 to the 2/3 power. That 3 that's in the denominator is going to be rewritten out into the front, and that becomes my index. And that is how you rewrite. That's it. All you're doing is rewriting. So again, what I do is I look at that denominator and that rewrites out into the front for each of these. So I want you to take a moment and rewrite the next two. All you're doing is rewriting. We're not doing anything else, just rewriting. Okay, that's our first step, is just a rewrite in radical form. Now, let's simplify if we can. One of these is super easy to simplify. Which one is super easy to simplify? What's it become? Yeah, the square root of 81. It is 9. For the next one. Well, I'm going to show you a little math magic. Here is some math magic. That if I have something like x squared to the third power, guess what? That is the same thing as x to the third power squared. They both are x to the sixth power. You see what I can do? See how I can switch these two numbers? Everybody see that? That's called math magic. So when I look at this, 16 to the third power, I have to the third power, so that's not helpful if I'm trying to rewrite things to the fourth power. So here's some math magic. If I want something to the fourth power, I can go look down the fourth power column. Is there something in the fourth power column that is 16? What? What? 2. So this is the same thing as 2 to the fourth power. And I didn't change to the third power, it's still there. And then guess what I'm going to do? I'm going to switch their places because that is math magic. So that's the same thing as 2 to the third power raised to the fourth power. And if I do that, that to the fourth power will cancel. What is 2 to the third power? 8. We could do that same super fun math magic with the first one. So I can't turn a 2 into a 3, but maybe I can find 64 in the to the third power column. Is there anything that is raised to the third power that would give you 64? 4. So let's try and rewrite it. So 64 is the same thing as 4 to the third power squared. And guess what? I'm going to do some more math magic where I can switch the place of those exponents. So that's the same thing as 4 squared to the third power. And guess what? The cube will cancel and I can rewrite it out into the front. So it equals 4 squared. What is 4 squared? Yep. We got a little bit more. Example 5 is just writing using rational exponents. These are not, we don't simplify, so we're just rewriting. So when we rewrite these, you've got to take that index and you need to rewrite it as a denominator for everything. So for anything that is there. So the first one, the only thing underneath the radical is a 15. So it becomes 15. The 3 was already there, and you put the 4 underneath. That is done. There's nothing else we're doing. We're not simplifying these. For the second one, we have 2 things underneath the radical. We have a 7 and we have an x squared. The 7, what is it raised to the power of? It's not there, but it is raised to some power. What is the power? 1. So that becomes 7 to the 1, and you bring the 3 underneath. And it's hard to write exponents as fractions. You just have to write them as tiny as you can, or make your base, make it a bigger number. And then the x, it has a number already there. It's a 2, but I've got to bring that 3 underneath. If that fraction could reduce, should I reduce it? Yeah, of course. And the last one, there is a 3. What power is it already raised to? 1. So just rewriting with rational exponents. Remember, a rational means ratio. Ratio is fraction. And last, write each expression using rational exponents and simplify. Okay, so here's what that will look like as we simplify using exponents instead of radicals. So the first one, we can rewrite it. It's going to have that 4 come underneath the 3. Well, how do I simplify? Well, what I wanted to do on the front page was rewrite stuff to the 4th power. I want to do the same thing. So can 81 be rewritten as something to the 4th power? So look down your 4th power. Can 81 be rewritten as something to the 4th power? So we're going to rewrite it as 3 to the 4th power. It's still raised to the 3/4. This is some side work to show you what happens if I have 4 times 3/4. Remember, 4 is a whole number. It's the same thing as 4 over 1. The 4's cancel, and you're left with just a 3. So here, if I have 3 raised to the 4th power, and then it's also raised to the 3/4 power, these exponents multiply, so they cancel. So I'm left with just 3 to the 3rd power. What is 3 to the 3rd power? 27. Very good. The next one, our first step is to rewrite. So the 5 has to come over here. It's already to the 1st power, so it becomes to the 1/5 power. The way I would reduce it is to look down my 5th column to see, is there something that can be raised to the 5th power, and it gives you 32. Yep. So the 5's will cancel, and you are left with 2. The last one, it is a square root, so that means I need to bring it out to both of them. So I get 121 to the 1/2 power, and then x to the 2/2 power. So 121, can it be rewritten as something squared? 11. And then what's 2/2? To the first power. So 11, we get 11x. We probably could have been able to do that just by looking at the square root, because I know that 121 is 11 squared, and I know that x squared, it cancels operations. So you can reduce things by writing them as rationals, or you can reduce them just using properties of undoing a whatever root it is, the nth root. Back to this. Do you guys feel more comfortable? Do you think you could do these now? What about the first one? What is the square root of 9? 3. Yeah. What about the fourth root of x to the 4th? What does that equal? What about the rest of y'all? What's the second one equal? Just x. Okay, what about the square root of 8? It's not going to go evenly, but there is a perfect square that can make 8. Which perfect square? 4. So it ends up with 2, square root 2. What about this one? Could I reduce this exponent? What's 4 divided by 2? 2. So what's 3 squared? 9. Hopefully we could do all of these now, and we feel, hopefully for those of you that moved from the not at all comfortable, moved up to somewhat, and those of you that were somewhat moved to the very, that you could at least do these problems. We don't have that much time, so you are free.